And we noticed that the formulas for confidence intervals were very similar. So one was for estimating population mean, and the other was for estimating population proportion. So for population mean, I needed to take a sample mean and then add and subtract the product of z times standard deviation divided by square root from n. And then for population proportion, I also had to add and subtract the same exact expression. And that same expression was, again, from sample proportion minus z times the PQ over n, the square root from this type of structure, right? And we had that, of course, all coming from samples. So we had that PQ with a hat, and also on the other side with a plus sign, the same exact expression. So these formulas don't look very nice, but when you start using them, you see that they really all about just one thing, just about getting this left side, and then to the right side, you get sign change. And that's basically all it was. And we also noticed they use various levels of confidence. So we can try an exercise, try to check the place where those levels of confidence were. And they were in the tables for z-scores down on the bottom. So whenever you have a particular level of confidence given, then corresponding z-scores will be what we use in those formulas. So that's why they're called confidence intervals. So we find the interval with particular level of confidence. So I'll try a problem so we can see how it's used. Maybe problem 35. I just open, actually 35 I'll do later today. I'll get something from beginning first. So how about one from before? And to find confidence interval, let's say an exercise number 25. Confidence interval for population proportion that talks about the insurance institute that wants to estimate percentage of drivers who drive a car while impaired because of alcohol consumption. So looks like that's what they want to do for the group of males in between 18 through 20. So they consider in this exercise 25, which is here on the page 338. We're in the section 2 of chapter 6. So dealing with the data that talks about number of elements in the sample equal to 42,772. And 5.1% said they drove the last months with being under the influence of alcohol. So probability or percent is 0.05 for 5%, and that's another one, that's 5.1%. And that's for the sample, so I put P with a hat. So please notice the formula that we're going to use is the one up here that requires me to also have two more numbers, Q, which is a complement of P. So Q with a hat will be 1 minus P with a hat as usual, and that's 1 minus 0.051. So this is 0.949. And then they also want to know the 95% level of confidence. So confidence gives us that z-score, and that's the last piece of data that I need. And for confidence of 0.95, the z-score is 1.96. And if you wonder why, well, I memorized it, but you can take a look at the tables and right away you're going to see this fact that 196 here, right, corresponds to 0.95. That's the most popular level of confidence. So now we're going to enter all the information in the formula above very carefully. So let me put 0.051, subtract the z-score 196, right? And then we multiply this by the square root from 0.51. That needs to be multiplied by 0.949. Okay, that's the Q, and divided by that big number, 42,000 something, 42,772. Here's the left side. Now for the right side of this estimate, I will be doing the same thing, but put a positive sign then, and that's how we are going to go about this. So let us calculate. Let's use calculator here. So let's see, 0.051, and we subtract 196 from this. And this is multiplied by the square root, so big square root, 0.051. It looks like this sections, they get more and more involved with calculations. 0.949, right? And this is also divided by this 42,000 something, 42,772. Please notice that all of these numbers, they have to be estimates for the proportion, so they should be in between 0 and 1. So there are some decimals, like mine here is 0.049,489 ... So I got a one side for this. To get the other side, I need to change my negative sign with a positive sign. So in my calculation, I'm just gonna add this. I'm gonna just replace the minus with a plus like that. And we're gonna have another side, 0.5308. So proportion of young males that drives under influence is somewhere in between 0.49 and 0.53 approximately. So which value should we consider for estimate for general population, for everyone? Well, looks like we should take the worst case scenario, and the worst case scenario is when probably more people are driving under the influence, right? So in this particular case, I can say that's probably about 5% or 0.053, because if you get a lower and lower and lower end, you may say, oh, nobody does it. Well, that's not going to be true. In fact, we always want to see the worst situation. So in some cases like here, the worst will be larger number, or in the other problems that we observed before, the worst case was a smaller number. Let's say you're trying to get a loan and they estimate your earnings. They've been on the safe side by the smallest possible, so they trying to be very, very conservative when they think about giving the loan to someone. So that's why we just go with the lower values. Well, once you had the problem done and use this formula, then I guess it's really kind of the same thing for all, right? And if you redo problem carefully, then you will see that other exercises pretty much same, and you may just change the level of confidence a little bit, and that's about it. Other things will be pretty much the same. So the power of story is that based on the sample, you calculate information about the sample, such as a proportion. You're making estimate about everyone, about entire population. So it's quite a powerful results. If you don't have any information provided, well, then you produce this information by looking at sample proportion and make an estimate for the entire population with a level of confidence, in this case, 95%. So you're 95% sure that 0.05 is our population proportion at worst case scenario. I say, but that's 95%. What if it's not correct? Yeah, whenever we're 100% sure, we always make estimates, turns out, in statistics. And to be 100% sure, you just need to consider entire population. And from there, you could get the exact value. But since you're making an estimate, then that's the best you can do. So notice that this interval, one may say, and this exercise, maybe it's fine because it's like close to 0.5, 0.05 anyways, but sometimes people say, you know, the estimate is not very good because you went too far to the left or to the right. So should I go 0.49 or 0.050 or 0.51? So which value is that? In other words, we have a so-called error that should be smaller. So that way we'll be given a better estimate. And for this particular situation, what I add and what I subtract is called an error. And this error, which is equal to z times square root from p q over n, needs to be lowered. And the question is, how can I possibly lower the number? And the answer is, it's standard. You want to divide by bigger, so the result is smaller. For example, if you share some, say, food with two people, well, yourself and your friend, well, you get like a half. But if you try to share it with 1,000 people, well, then you get pretty much nothing. So the larger number of people you're sharing it with, the less you get, right? So the idea is that the sample size, if you want to get smaller results, should be larger. And of course, the ideal case is it's as large as a population, but sometimes you don't need to consider entire population because it's too much work. And that's why the question is, what would be the reasonable size of the sample to select? So my error will be smaller. In other words, if I try to pull from this formula the sample size in, and looks like if I squared both sides here, so if I squared, so I don't have a square root, right? So I'll just get p times q divided by n. And then if I use so-called proportion rule, so if I multiply by n and divide by r, so if I have z squared times pq over the square of r, then I will get exactly the sample size I need. And that's actually the formula that they have in this section, which is related to finding the sample size. So your interval is not going to be very large. So your interval will give you the reasonable estimation. Because you might get interval which is from 0 to 100%, and you say, yeah, I know it's a percentage from 0 to 100%, but what is a better estimation? And that's the whole point of this process. So I was just trying to justify the formula they used in this section, and maybe now I can take a look at the exercise I was about to do first, and then I said I'll do it later. So which one was I trying? Oh, 35. Let's do 35. So it says, if you got hired by the company to do some research, and they want to estimate the number of households in which a vehicle is owned. So how many households do you need to survey to get a 94% confidence, and the error is 3 percentage points. So what they want is not to be dealing with very wide interval. Just like in this case, the error was pretty good, but they say, okay, what about if error is 3%, which is 0.03, right? So that's exercise number 35. So the question is, how many, or what is the sample size you need to survey? Notice that it's probably expensive somehow for people to do survey because they need to pay salary to surveyors and etc. So they don't want to survey too many people, but if they don't survey a lot of people, then their value of that research will be nothing. So they decided that they want to be within 3 percentage points, and the level of confidence they want is close to 95%, but for some reason they decided to go with 94%. Okay, we can do that, of course. So 94% confidence, remember, that's the portion in the middle of interval. So remaining 6%, right? 0.06 will compose those two so-called tails, and each tail then will be of the size 0.03, because 0.3 and 0.3 total to 0.06. And we also know that the z-scores will be on the opposite sides of 0 because picture is always symmetric. So I find one and the other be the same, but with the opposite sign. I think we already did it once, time before last or so, this setting. So I'm going to the tables, and I need to find 0.03 there among the areas. So that should be on this side of the table, right? And as usual, if I start on the top and scroll down, I'll see the areas are being increased, and 0.03 looks like it's going to be somewhere in this row. And notice if I keep going to the left, I will get the place where 0.03 has to be in between, right? We always get the closest. It looks like 0301 is definitely going to be closer to 03 because the other is like 6 of these 10,000s away. So I'll get a row and the column estimate for this particular z-score. Notice the z-score is not in the tables and not in that little chart because we don't have such a value as 94% in it. It's unusual value. So minus 1.8. And then the column gives me another 8. 188, and the other is plus 180. So for the z-score, I'm going to use 198 because we usually take the one with a plus sign. When I say, Alex, I want to take one with a minus sign. You can do this, it doesn't matter because z is squared anyways, right? If you take negative, you square it and it'll become a positive no matter what. So I just want to show you that there's not such a number here in the critical regions that they give. They just give us confidence 90, 95, or 99. And for the other level of confidence is like the one that I just have in 35. I need to get that z-score myself. Well, that's fine. We can do this. So I already know what is going to be the error. So I already know my denominator. I already know what is z. The question is, what about p and q? They didn't give it to me. And they say, if you're not given p and q, you're making your best estimate, which is 50-50. The reason why is because the p, the proportion or probability, is always on this interval. And to get the best guess, the best estimate, I should take 0.5, the point in the middle, the average, and that's what I can do when we're not given that proportion. I say, what if I take 0.3, for example, from my estimate? Let me do it in different color. Well, if you take 0.3, but what if it's in reality 0.9? So then you're going to be off by like 0.6. But with 0.5 and 0.9, you'll be off just by 0.4. So you'll be closer. See, we're always trying to get the best possible estimation. And looks like for this case, I have to take 0.5. And that's what they say in the book. So if you're not given that P, then automatically it's 0.5. So Q is also 0.5. So we get that 50-50 kind of thing. So now I plug in the formula above, which is right here. Instead of Z 1.88 that I square, then we multiply this by 0.5, and then again by another 0.5. And then we divide this by square of error, and they gave it to us. That's 0.03. And we'll get the sample size. I just want to make sure I put squares here. So let's put this in a calculator. It's too messy. Let me clean this a little bit first. So it looks like we need to use a calculator again, as usual. So please try to put this in your calculator. I hope you will be able to do it even faster than I, right? So I got this times 0.5, another times 0.5, and then divide this by 0.03 squared. So this is the number of sample elements you need. This 0.98177. So you go with sample size 0.982. Well, because you cannot take the sample with fractional number of elements. That just makes no sense, right? So sample should always have a whole number of elements in it, because otherwise you just cannot take 0.77 of the element. That's just not possible. So we round, and turns out we always move to the next place. So just move to the larger one, to 982. So for that particular case, you want to get the estimate for the particular confidence interval. You take a sample of size 982 if you're not given P and Q. Now, when I look at the part A, I just noticed that they actually gave us a P, and that's much better because now we get a much better estimate. So let me do part A now. So I will repeat exact same process again, but with a different value of P and Q. So I just didn't read part A. I thought that was already the whole problem for some reason, but it's actually part A here. But that's fine, because I think we will see exercises with no given initial estimate at all. So we'll use 0.5, but now we'll be able to see how much we improve. And improve here means less elements for the sample, right? Because to consider 982 sample elements, well, it's time consuming. But if you use a better estimates, then you will see that it's going to be a little bit less sample elements. So now I'm going to do exact same thing as I just did already here. So I put 188 squared on the top and 0.03 squared on the bottom. But now I'm going to replace these 0.5 and 0.5 with times 0.86 and times 0.14. And we'll see that definitely we're going to have less sample elements to deal with to produce that same level of error. So let me re-enter the whole thing so we better see it. So 1.88, and then I go times 0.86, and then again times 0.14, and then we divide by 0.03. We already know that it doesn't matter that we don't have this number such as 188 squared and 86 and the entire numerator, but it's the same thing because when we multiply, they go to numerator anyways. And notice that now the sample size is like twice smaller, 473, which tells us that it's a good idea to make an estimate first. And one is, but how can I make an estimate? Well, you can start collecting your sample. You can select like 10, 20 elements, and then calculate whatever you need, which is proportion of households that have car. And once you made an estimate already, then based on that estimate, you will definitely save you twice more time or twice more funds if you go instead of 980 to 470, right? So that's definitely half of work to do. And that's, I think, very useful for practice observation. Well, the problem is not over. They have part B and C here, so let's see what they want. Assume that there is no available information So I actually did part B of this exercise first. See, because they say no available information, but now we know that we better have some available information. So instead of going for 900 element sample, maybe you collect 30, 40, so, and then stop, and then based on this 30, 40 estimates, you will be able to actually get way, way less sample elements. And that's the idea. So probably when no available information is there, you wanna, well, get something out of smaller sample first. So that's the message. So using this 0.5 and 0.5, very crude estimates, you probably don't want to go with this. Finally, part C says, assume that instead of using randomly selected household sample data are obtained by asking readers of Washington Post to mail in survey form, is the result going to be affected or not? Well, a random sample, remember we talked about random sample in the very beginning of this class. That's the best possible sample that actually shows entire population of households in very detail. And if you just survey people that read Washington Post, so they probably could be most likely somewhere in Washington, DC, or at some people that read that type of newspaper. Well, there are some people that don't read this newspaper. Maybe they don't read anything in English at all. So that way you're going to lose that portion of population. So you better always state that this data is for readers of that particular newspaper. That way you'll be on a safe side, right? Because if you go to some other community or some other state and try to tell that your research also includes people from that state or from that country, then it's probably going to have nothing to do with that population, and it simply could be totally wrong result. So you want to always be careful with selecting your sample, and I guess that's what part C of this exercise is talking about. So finding the sample size is always a first step when you're trying to get your confidence interval, because again, you don't want to get way too wide confidence interval within some reasonable boundaries. So before doing the next exercise, I'd like to tell you our schedule for the later weeks, because remember, I was a little bit frustrated that some people did not turn in their work, and they still waiting actually for some people in class to turn in the work from me. So looking at what's happening right now and what's left for us to cover. So today is already the 17th of November, right? And we have one class on 22nd. Let me clear this. So that'd be a Thanksgiving week. So we don't have class on Thursday, but only on 22nd on Tuesday. Then we're going to have another class on 29th, the following week. So that'd be last class in November. Then one more class December 1st, and I propose to have a final exam on the 6th, because I think we're pretty much finished with covering the material. I need chapter 6 and 7, and chapter 6 we'll finish up with soon, and with 7 we're already done. So I guess 2 more class meetings will be plenty to finish up with chapter 6. So we'll do it on 22 and 29. And then on the first, I'm going to do a review before final. So I will send you the final exam in exact same format as I did with a midterm. So it'd be not really a final, but the second test number 2. And I want to run it on Tuesday, the 6th of December. So this way I'll be able to grade it on Thursday, the 8th. Before that time, I will post grades on the Blackboard as usual. So then we can discuss it the following class meeting. If you want to discuss it, if you don't get the grade that you wanted to get. And I will tell you what to do to fix it. And this way we'll have plenty of time to actually fix it. So, because otherwise, if I give the exam by the very end of semester, and that's what worried me a lot, because I noticed that something happens and lots of people simply don't send me their work on time, and because of various circumstances, and I didn't feel like downgrading people because of that. So I'm going to give final on Tuesday, and the coverage of material allows me to do this December the 6th. So we'll do plenty of review for that. And that's our plan till the rest of semester. I want to tell you also the homework, so you can finish up with it. So let me go back to the textbook and let's see what we covered since the midterm. So it looks like we started with chapter 4, and in chapter 4 we did only 2 sections, 4.3 and 4.4, right? Then we moved to chapter 5, and there we did sections 5.2, 5.3, and then 5.5 and 5.6. So 5.2. So these sections are already done. I hope you have already something for those sections. So 5.5 and 5.6. So these are chapter 5 sections. Now we're in the chapter 6. Oh, chapter 6. So we're dealing with the estimating the population proportion. And then we already did 5.3. So I'll also look at 6.4. So 6.2 through 6.4. That's from chapter 6. That's one more section I want to do in it. And we also looked at 2 sections in chapter 7. Yeah, if you do a couple of problems from each section, that'd be perfect. That'd be perfect because all problems there are very, very similar. So if you know how to do 2 problems, you know how to do the whole section. Even if you know how to do 1 problem, then you already know how to do the section. So I'm going to ask you for 7.3 and 7.4. That's what we did also, right? 7.3 and 7.4. So these are the sections that we also already covered. So right now we're in section 6.2, and we already looked at section 6.3. So I will, of course, look at it again a little bit next time. And then section 6.4. So go 6.2, 6.3, and 6.4. So these are the sections that you should hopefully do before the final exam. And I guess that's all we need for the class. So I'm gonna return back now to page with section 6.2, so it's about 330, something like that. So when we estimated the sample size, and it looks like I want to do another calculation, and maybe have you try to also calculate the sample size here. So I can do problem number 17 exercise, because with this 94 level of confidence, it's pretty odd. Usually level of confidence is standard, like 99 or 95. That's the most popular confidence level. So if sample size is 400 and we have x equal to 300, which means that the sample proportion is 300 elements out of 400, which is 3/4, right? Or 0.75 here. So they decided not to give us a p hat, they just say 300 out of 400. Okay, let's divide and we get that p hat. So right away I can get a q, which is 1 minus 0.75, the complement, right? That's a 0.25. And also we are given that the confidence, they want to construct the confidence interval. Okay, let's construct the confidence interval. Confidence interval with a level of 95% will give us a z-square, which is equal to, remember, 196. Let's check out this little chart once again, right? For 0.95, it's 196. So z is 196. So I get an interval from the formula that says p hat minus z times pq over square root of n. So pq over n. And then on the other side of this, we need to get a p hat plus, right? Z, and that's again pq over n, like that. So let me calculate the left side, and then you can calculate the right side. So what I do is I put 0.75 minus z, which is 196, multiplied by square root from p cubed 0.75 and 0.25, right? To multiply these guys together. And divide by sample size. What is the sample size? Well, they said it's 400, right? So sample size is 400. Let me write it. Didn't write it, so write it. Sample size 400. So we have 300 out of 400. So that's for P, the left side. And what you need to do for the quiz, do the left side. So it's the same thing, but with a plus. So let me show you how I enter this in my calculator here. So we go with a 0.75 minus 196. And then I times this by square root. And again, 75 times 25 divided by 400. So here's my left end for this interval. It's a 0.707 dot dot dot. And for a quiz, please find the right end. What does this mean? Well, you need to calculate exactly the same thing, right? But instead of minus sign, you need to enter the plus sign, because formula is the same, but we need to enter the plus sign. So find this side of confidence interval. So you do same thing, same calculation as I just performed, but looks like you just need to change that minus with a plus. So this be a just practice to use your calculator, the calculator exercise. I just want to make sure that you can enter these numbers in a calculator carefully. So please try. That's our quiz.